Hello, and welcome to my presentation on a single-state passive vibration isolation system for scanning tunneling microscopy. My name is Toan. I'm a master's student in the Mechanical Engineering Blended Program, which means that I'll receive both of my bachelor and master diploma at graduation. Uh, at school, I enjoy dynamics and computational methods. Outside of school, I like to look for discount tickets to musical and enjoy any type of comedies. After the presentation, if you have any questions for me about the topic that I present, please reach out to me at my school email. For the presentation today, I'd like to break it down into four main topics. The first one is the introduction to the scanning tunneling microscopy, or STM, and a specific type of STM called the lighting STM, named after a professor that invented it. The second one is the dynamics and vibration analysis that analyze the mass spring system that the STM will stay on. And the third one is the finite element analysis, where we will look into the housing structure that will hold the mass spring system. And the last topic is the magnetic damping analysis, where we'll look into the interaction between the magnets, the permanent magnets, and the copper state of the mass spring system. So for the scanning tunneling microscopy, it was first invented in the 1980s by four scientists in the IBM lab in Switzerland. Two of them, Binnig and Rohrer, were later awarded the Nobel Prize in Physics for the invention of STM in 1986. The picture on the right here shows one of the first few scan images of the gold surface at room temperature. The SDM operates on the quantum tunneling effect to study the surface of materials on atomic scale. So the tip will scan over the surface of material where the distance between the tip and the surface is only a few angstrom to a few nanometer away. As a result, the device is very sensitive to any types of ambient noises and vibrations. So a vibration isolation system, or a VIS, is very important to achieve the high resolution of the images. Um, the two animation we show here, called the constant current mode and constant high mode, show two modes typically used for an SDM. As the name suggested, the constant current mode keep the current as a constant and let the height of the tip to the sample varies. Um, uh, in contrast, the constant height mode just scan through the surface, keeping the height at a constant level and record the current to map out the surface of the material. Notice that the current here is only in the scale of picoamps, so you need to amplify it a lot to actually get the data that can operate with. The constant height mode is it's very fast, but at the same time you can easily crash this tip of the STM into the material, whereas the current mode is slower, but you can get the high resolution of the image. The lighting STM is one of the designs for the scanning tunneling microscopes that exists out there. The lighting STM invented and patented by Professor Joe Lighting from the University of Illinois. That one of my advisor have the opportunity to work with for his PhD. The lighting STM is a robust design where you have two tubes, the outer tube and the inner tube. The outer tube connected to the sample holders and the rails to move the sample closer, and the inner tube will perform the scanning operation. If you can see the picture on the left here, this show the rails sticking out of the aluminum box that hold the inner and the outer tube. So the two pictures on the right show the scan images from the lighting SDM with the scale of 400 by 400 angstroms. The red dotted line here is about 20 nanometers, and the two white line, those are actually the carbon nanotube on the surface of graphene. You can see that from the first image in the 1980s to now, we have gone a long way to get the high resolution images from the SDM. So to design a successful VIS for those SDM, we first analyze the mass spring system to hold the SDM. We will look at the dynamic equation for the vertical mode. This is one of the 6 modes that occurs in the VIS. And the reason that we look at the vertical mode only now, because we want to derive the relationship between the spring stiffness and the mass of the stage, so that we can purchase the spring from some vendors online. So the first equation here is a very typical equation you see in dynamic and vibration. So X is the coordinate system attached to the state, and Y is the coordinate system attached to the frame, where MEQ is the equivalent mass of the stage, CQ is the equivalent damping for the vertical mode, and this will be dealt with in the magnetic damping section. KEQ is the equivalent spring stiffness for the vertical mode. So the natural frequency of the state can be derived as the ratio of KEQ over MEQ. And N is the number of springs that we use. K is the stiffness of one spring. Phi is the angle of this spring with respect to the surface of the stage. And M state is the total mass of state. And the reason we have the angle spring configuration, because we want to add some torsional stiffness to the stage without actually adding the torsional spring, because torsional spring will add another method, another means for the vibration to travel through into the stage. So it will complicate the design a lot more. The VIS with mass spring system is a base excitation system. With the plot here that we can see is the displacement transmissibility for base excitation. And the vibration isolation occurs right here when the curve go below 1, the ratio of the input over the natural frequency. So the ratio here occurs at about square root of 2. And a lot of literature shows that the input frequency from the vibration of the floor, from people walking around, is from 1 to 100 hertz. So we need to design a mass spring system to effectively isolate the frequency, the input frequency from this range. If we rearrange the equation, the ratio of the input over the natural frequency, we can get the relationship between the mass of stage and the stiffness of spring, so that we can use this equation to select the springs from a couple of vendors online. The two figures here show that the spring selection process that we use to pick the spring for a 14-inch high vacuum chamber. All of the solid lines are the relationship that we derived earlier, and each of them represent a input frequency, and any data point here will be the spring data that we got from the vendor. So I download all of the spring data and we plot it here. So I can show that these data points, as long as it's above a solid line, so that means that to represent that the spring can help isolate the frequency up to that frequency. For example, if a spring data is above 1 hertz, like this data point, it means that it can isolate the vibration up to or down to 1 hertz, and any frequency above it, 1.52, 2.53, and higher than that, that can successfully isolate those frequencies. Whereas if you pick a data point far below here, it won't isolate the frequency high up in in the plot, but it means that it cannot go down to the low frequency range. So the analysis show that the low frequency spectrums are actually are actually the challenging region for the mass spring system. And during the experimental process, when we construct a wooden stage and we have the A-spring configuration of angle springs, and we vary the mass of the stage on a shaker and collect the data in the spectrum analyzer, we can construct the experimental data plot here. So the left one is the absolute magnitude. So we can see that as the masses, the if we increase the mass on the stage, the natural frequency goes lower. So this is actually what we're predicting in the analysis model. And in the dB scale, when it gets below 0 on the dB scale, it means that we achieve the vibration isolation. And it can be seen here that the vibration isolation occurs between 1 and 2 hertz. So it means that the more weight we put on it to the target weight for this spring, it should be about 7.5 kilogram. We should get to the natural frequency to be lower than 1 hertz, and it will cross the horizontal axis at about 1 hertz. So the theoretical model is correct. But one of the few problems we observe is that with the symmetrical A-spring configuration, the state will wobble a lot because when the stage gets heavier, the wooden frame is very flimsy. So it doesn't go up and down. The frame doesn't go up and down anymore. It actually move from side to side, and it disturbs the vertical mode that we're trying to test. So that's why you see the yellow curve is actually it's a little bit more noisy than the other line. So that gives us hint to redesign the configuration from A-spring to 6-ring. So with 6-ring is a non-symmetrical system, so it can actually split between different modes and utilize all of the modes and the non-symmetry of the problem. So if the state wobble or rocking from side to side, we can split that mode into the vertical and the yaw mode, the rotation mode. So once we have the experimental data, we can proceed with buying the actual spring to be used in the vacuum chamber made out of stainless steel, because the music wire material has a higher outgassing ratio than stainless steel. So the final spring should be made out of stainless steel. And for the copper stage or the mainstay, we should use copper because it has higher density than aluminum. So it will save a lot of volume in the small compact vacuum chamber. And the copper will simplify a lot of the designs when we use permanent magnets on the bottom of it to damp the mass spring system. So now let's look at the housing for the mass spring system. There are 3 designs, and these are infinite degree of freedom systems. So we have to use FEA to study the natural frequency for these. The first iteration is one of the designs, original design, where the original design has 4 vertical rods, and we try to use 6 of them to increase the stiffness. And the second one is inspiration from a CubeSat design, where you have these 90-degree angles at the 4 corners. And the third one is a solid hollow tube with some cutout windows to look into the state and to operate the states. And the reason we want the housing structure to be very stiff because we're trying to create like a high pass filter. So only the high frequency can go through the housing. But then in the mass spring system, we try to make it a really low pass filter. So like at about 1 or 2 hertz. So all of the input frequency from 1 to 100 hertz can be naturally filtered or isolated with the existing system. So we need this housing structure to be as stiff as possible. And with the 3 frames, we put into the simulation in SolidWorks, and we observed that the third frame actually have one of the highest natural frequency for each mode. So we proceeded to do a detailed FEA study for this hollow tube. And the first natural frequency is about 540 hertz. Uh, so that's well above 400 hertz. And if we put the cap on top and the bottom, we should expect the natural frequency to be a little bit higher because we'll restrain the mode shape for the first mode. So this design proved to be effective when we want a stiffest frame for our intention. The damping method to be used for the housing structure is that we're going to use some Viton gasket to sandwich between the top cap and the hollow tube, and the hollow tube to the bottom cap. So Viton is a viscoelastic material, but unfortunately we couldn't do the some experiments to extract the data for viscoelastic material. But luckily, there's one research paper that study the Viton specimen purchased from McMaster-Carr, which is also a website that we're gonna use to buy the Viton from. And they study the hyperelastic characteristic of this material to characterize it as the Munif-Riflin hyperelastic material. So these data point will help plot the curve, and the least square fit for this data point help extract the 2 constant, C10 and C01. These constants will be used in the FEA software to model the hyperelastic material of Viton. And we try to avoid the linear elastic model because with the very high Poisson ratio of Viton, about 0.49, 0.495, it can easily break the FEA model. So with these data points and with the understanding that the system will be used at room temperature, we can model it at the hyperelastic material and study first the natural frequency of the Viton gasket, where there will be 2 options to purchase from, the 1/8 inch gasket and 1/16 inch gasket. And it can be shown here that the first natural frequency and the following natural frequency of the Viton gasket, the thicker one will have a higher natural frequency. So this indicates that we should go toward the 1/8 inch gasket because this have a higher natural frequency. So we try to push, remember we try to push the housing frequency to be above, very as steep as possible, above 100 hertz. But then we also need to study the damping characteristic of these 2 versions of Viton gasket. And it showed here that when I did the model dynamic transient response in Abacus, of course the thicker one will have a better damping characteristic than the thinner gasket. Is actually a lot more than the thinner one. The model dynamic transient response use an impulse. So you input an impulse into the model, and it will record the time response of one node in the FEA software. And this is the plot that we receive. So with the natural frequency study and the damping study, it indicates that we should pick the thicker part, the thicker gasket of the two. Now we move to the last section of the magnetic damping analysis. So there's a couple of theories that we can use to model the permanent magnets. One of those is called the current method, the equivalent current method, where we use the magnetization constant of the material, that's M0, and the magnet length to figure out the equivalent current of the magnets. And these two equations right here that show the polar or the radial components, or the longitudinal or the vertical components of the magnets. And these equations can be found in a couple of research papers by Ibrahimi or Giordano, and in the textbook shown by Craig. These equations, the inputs are R and Z, which are the input coordinates to be used in the equation. These coordinates numbers, they are above the surface of the magnet. Mu0 is the constant of permeability of free space, so that's a constant. Radius of the magnet, capital R, is a constant as well. And the variable in these two integrals are Z prime. K and E are function of K, where K is again another function of capital R, radius of magnets, and little r and Z, where it's input coordinates of the magnet. So K and E's are complete elliptic integrals of first and second kind. These are built-in function in MATLAB. So we can use MATLAB to calculate these, and then take the output of K and E to input into the functions, where we code in the numerical method to integrate this fairly complicated integral. And these are the results. So I use the numerical integration routine with the Gauss-Legendre quadrature rule with 7 integration points. So what that means is, if I put a coordinates point right here above the magnets, I can figure out the number for that coordinate point, and then I'll input that into the function, where remember that I'll calculate K and E, and then also doing the numerical integration at that point. And the numerical integration at that point simply means that we will evaluate the integral at a couple of points, and then we add up the number at those points together to get one data or one number for this specific point on the spatial coordinates above the magnet, and we will loop it over the spatial above the magnet to get all of the flux density here in the plot. So the question is that, how do we know that the coding routine that we did is correct? So it turns out I have to use another software called the Finite Element Method Magnetics, FEMM software. And the picture on the left here show the little magnets in a confined region to get the flux density plot. And when I extract the data at the surface of the material and 15 millimeter above the surface of the magnet, I can plot it against the MATLAB, and the simulation show that these data point, they agree pretty well. So it means that we can get the magnetic flux density B pretty well from the animation from the calculation from MATLAB. So we can use this to calculate the next step, which is the damping coefficient and damping ratio. So the equation for the damping force is calculated from the current density J and the magnetic flux density vector B. This comes from Faraday's law. And when we carry out the equation, we can see that the force is in fact a function of z dot, which is the vertical velocity, and theta dot, which is the rotational velocity or the yaw velocity. Because of this, the force, the damping force caused by the eddy current or the magnetic damping can be classified as the viscous damping because it depends on the velocity. So in this equation here, sigma is the conductivity of copper, delta is the thickness of the copper stage, R inner and R outer, those are the inner and outer radius of the stage. So if you have a solid stage without any holes in it, then R inner equal to 0. And we'll feed the data we got from BR and BZ from the previous calculation into another new function to calculate for these forces. Specifically, we calculate for C vertical and CR. And these have the units of Newton second per meter. So with the damping coefficient calculated earlier and the natural frequency that we calculated from the dynamic and vibration analysis, we can calculate the damping ratio because the damping coefficient divided by the critical damping is equal to the damping ratio. And we can plot the damping ratio as a function of the gap distance of the surface of the magnet to the copper stage. And we can also simulate how many of the magnets to be used. Notice here that there's a couple of assumptions that we need to make. Specifically, you need to put the magnets in a pretty much far away from the edge of the copper, because otherwise it will mess up the calculation. And we have to use a method here called the imaginary current density, because you see that at the very edge of the material, it doesn't go to 0. And that's actually a wrong assumption. We need the current density to go to 0 when it at the edge of the projected conductor or at the edge of um, the copper state, because otherwise you don't have the current outside of it. So you need to subtract the imaginary current density outside of the something called the infinite current density to get the finite current density. And this is shown here in the plot where the yellow curve actually ends at 0. So make sure that our animation has the correct data points. And by looking at the displacement transmissibility plot again for the base excitation, we see that we only want the low damping ratio in the vibration isolation region, because too high of the damping ratio will get the curve to be lifted higher, and it actually you reduce the amount of effectiveness in using the damping, the magnetic damping. So we only aims at around 0.2 and 0.3. So according to this displacement transmissibility plot, we should aim for the zeta to be the damping ratio to be 0.2 and 0.3, at most 0.2, because 0.2 it will the differences between 0.1 and 0.2 is not that much, but at 0.3 the purple curve right here is a lot. So we should pick the damping ratio to be about 0.2, and from that we can determine the distance between the magnet and the copper state to get that targeted amount of damping ratio. So when we get the damping ratio that we want, the rest of it is just to try to simulate the response of the system using these equation that we had earlier. So for the vertical mode, the equation is very similar to what we have in the dynamic and vibration analysis. And we just plug in the zeta V, which is the damping ratio for the vertical damping coefficient that we already calculated, divided by the critical damping coefficient in the vertical mode. And this is a second order differential equation, ordinary differential equation for the vertical mode. And we will do the same thing for the yaw mode. And this is the equation for the yaw mode. Notice that here we have to add the R bar square term into the yaw mode, because C yaw out of the simulation for the damping coefficient, it has the unit of Newton times second per meters. So it's not the typical unit you will see for a rotational or yaw mode. So that's why you need to compensate by R bar, which is the distance from the center of the stage to the center of the magnet. And through a little bit of calculation, you can turn the equation into functions of the parameters of the spring, the radius of the stage, and um, the mass of the stage. And at the slide here, you can see that this is the animation I made for the vertical mode and the yaw mode. So you see that at the yaw mode, it reached to below 50% of the amplitude within 1 second. And for the vertical mode, it reached to be below 50% under 1 second. So for the simulation for the time response using ODE45 MATLAB, we can see that it's a fairly effective damping characteristic of the system. Remember, we don't want too much damping when we're already in the vibration isolation region. And that is it. That's 25 minutes of my presentation. I would like to thank the SAMPE University Research Symposium for giving me this opportunity to present my research to Capoli ME departments, and two of my advisors, Dr. Algendor and Dr. Scott, for helping me along the way. Thank you.